Good day, students. The third lesson in Module 5 is about molecular geometry based on VSEPR model. So what is VSEPR? This stands for valence shell. So valence shell electron pair repulsion model. Okay, so this predicts the geometry of the molecule from the electrostatic repulsions between the electron pairs. Remember that electrons are negatively charged. So when they come close, of course, they repel each other because like charges repel. So our bonding electrons and then bonding electrons also have repulsions or repel each other. So in VSEPR, we use this so-called class with A, which stands for the central atom, B is the atoms bonded, or are the atoms bonded to the central atom, and E are the electron pairs on the central atom. Okay, so we use here our X as the subscript for B, so that means how many atoms bonded to the central atom, and Y as the number of electron pairs on the, or lone pairs on the central atom. So let's start with AB2. AB2 means we have two atoms bonded to the central atom and we don't have lone pair on the central atom, so zero lone pair. That is why you cannot see a letter E in this class, because there are no lone pairs on the central atom. So the arrangement of the electron pairs here is linear. So we have our central atom and the two lone pairs here. Now if we replace this with an atom, so we have our B, which stands for the atom, the geometry of the molecule, or after accounting the repulsion of the bonding pairs of electron, we now have a linear molecular geometry. So its bond angle is 180 degrees. So that is how we write our linear molecule with class AB2. We have our A in the center, and then we have our two atoms bonded. So an example of a molecule with class AB2 is beryllium chloride. So we have our central atom, beryllium, and the two atoms bonded to the central atom, which are the two chlorine atoms. We don't have lone pair on the central atom, so that is AB2. Again, the bond angle is 180 degrees. Next, we have our AB3 class. So here we have three atoms bonded to the central atom, and there are no lone pairs in the central atom. So we have our three here, three atoms bonded. We don't have lone pairs in the central atom, so you can see any E in there. No? So the arrangement of the electron pairs is trigonal planar. So we have our three lone pairs, and the bond angle is 120 degrees. Now, if we take into account the repulsion, these are all non-bonding pairs of electrons. So if we take into account the repulsion of the electrons, the geometry of the class AB3 molecule is still trigonal planar. No? So there is still 120 degrees bond angle. Example of a molecule with class AB3 is boron trifluoride. So we have our boron in the center, and we have our three fluorine atoms. No? So when we draw a molecule of AB3 class, we have our A in the center, and then our three atoms bonded. Next, we have AB4 class. So here we have four atoms bonded to the central atom, and we don't have lone pair on the central atom. So the arrangement of the electron pairs is tetrahedral. When we take into account now the repulsion of the electrons, the molecule with AB4 class has still tetrahedral molecular geometry. So how do we draw tetrahedral molecule? Example of tetrahedral, by the way, is methane, We have our carbon in the center, and we have our 4 hydrogen atoms. So to draw tetrahedral molecule, we have our central atom, then we have one atom at the top. We use this broken line or dashed line for atoms projected at the back. So we have one atom at the back, and then we use this wedge line or thick line for the bond projected to the front. And then we use one line, so this is our wedge line, the thick one, and we have one line again for the atoms at the side. So this is our tetrahedral. Again, we use dashed line or broken line for the atom bonded or projected at the back, and then we use wedge line for the bond projected to the front. Okay, so in this structure, for example, this wedge line here is here, and this broken line here is here, no? Or it could be on the other side as well. So I mean, if this is where you put the broken line, this line here should be a straight line, but not wedge or not thick. You can also put the broken line here on the right and the straight line on the left, no? So again, when we draw a tetrahedral molecule, one bond is at the top, then one line on the side, one broken line which projects to the back, or that which means projected to the back, and then one wedge line or one thick line which means the bond is projected to the front. Okay, next we have the class AB5. So here we have 5 atoms bonded to the central atom, and there are 5 central number of atoms bonded to the central atom, and there are no lone pairs on the central atom. So the arrangement of the electron pairs is trigonal bipyramidal. Bi means 2. So we have 2 pyramids here, and it's trigonal, meaning our base has 3 points, 3 points. So our first pyramid is here, if you can see that. This is our apex, and we have our base in here with 3 points, no? So that's trigonal pyramidal. The second pyramid shares the same base, no, as with the first, no? And this is the vertex of the second pyramid. So we have our first pyramid here and another pyramid here. Now, after accounting the repulsion of the electron pairs, we now have still a trigonal bipyramidal molecular geometry. Again, we have our first pyramid here and our second pyramid, which shares the same base as with the first. Example of AB5 molecule is phosphorus pentachloride. So we have our phosphorus in the center, and we have the 5 chlorine atoms. The band angle here is 120 for the base. So we have 120 here, 120, and another 120. For this one here, we have a 90-degree band angle. Now, how do we draw AB5 molecule? So we have our central atom, and then one of the atom at the top, one at the bottom. Then we have our one atom here, and here we have our broken line, and we have our wedge line here. Okay, so that is how we draw trigonal bipyramidal molecule. So this must be broken line and this must be wedge line, because this is projected to the back and this is projected to the front. Okay, so these here are the base, no, of the pyramid, and this is at the top and this one is at the bottom. Okay, next we have class AB6. Here we have 6 atoms bonded to the central atom, and we still don't have lone pair on the central atom. The arrangement of the electron pairs is octahedral. This is like a square bipyramidal. So we have two pyramids, but instead of three points sa base, we now have four, or a square base, no? So this is our first pyramid here with apex here, and the second pyramid shares the same base as with the first. So this is our second pyramid. So if we take into account the repulsion, no, of the electron pairs, we now still have the octahedral molecular geometry. Example of a molecule with class AB6 is sulfur hexafluoride. So we have sulfur as our central atom, and we have 6 fluorine atoms bonded to the sulfur. The bond angle here is 90 degrees. Now, how do we draw an octahedral molecule? So we have our central atom, then we have one atom bonded at the top, one at the bottom. Now we have two atoms at the back, so we use two broken lines or dashed lines. And we have two atoms projected to the front, so we use two wedge lines, so one here and another here. Okay, so this is our octahedral. Okay, this is the base, no, of the octahedral, and these are the two vertices, no, of the pyramid. Next, we have AB2E. Remember, our AB3 has 3 atoms bonded to the central atom, and it doesn't have a lone pair on the central atom. Now, what if instead of 3 atoms bonded to the central atom, we have 2 atoms bonded now and 1 lone pair? So AB2E means 2 atoms bonded to the central atom and 1 lone pair on the central atom. Since there is only 1 lone pair on the central atom, so we don't have to write 1 in here, no? So as is lang AB2E. So the arrangement of the electron pairs is trigonal planar. But if we take now into account the repulsion, so instead of an atom here bonded, we now have lone pair. So we have lone pair, bonding pair, repulsion. If we take into account that repulsion, the molecule will assume a bent molecular geometry. Example of a bent molecule under class AB2E is sulfur dioxide. So we have our sulfur here and our 2 oxygen atoms bonded to the central atom, which is sulfur, and we have our 1 lone pair here. So how do we draw AB2E? Remember our AB3, so you have A, then our 3 atoms bonded. So this is AB3. When we have AB2E, one of that atoms bonded will be replaced with a lone pair. So for example, we will replace the atom at the top now with a lone pair. Okay, so this is now AB2E. We have our 2 atoms bonded to the central atom and we have our 1 lone pair. Okay, so this is how you draw AB2E. Okay, next we have AB3E, meaning we have 3 atoms bonded to the central atom and we have 1 lone pair on the central atom. The arrangement of the electron pair is tetrahedral, but if we account into the repulsion of the bonding and the lone pairs, we have a trigonal pyramidal molecular geometry for AB3E. So we have, for example, ammonia. We have nitrogen in the central atom and 3 hydrogen atoms bonded to the nitrogen, and we have one lone pair on the nitrogen atom. Now, how do we draw AB3E molecule? Remember, how do we draw, by the way, a tetrahedral? We have our A at the center, or central atom. Then we have our 4 atoms bonded. So one at the top, one atom with a wedge line, I mean a dash or broken line, one with a wedge line. So this again is projected to the back, this is projected to the front, and then one straight line, this is not straight, a straight line on the side. Okay, so this is our tetrahedral. Now when we have AB3E, the atom at the top here will be replaced with an electron. So we will delete that. We will delete this atom here, and this will be replaced by a lone pair. Okay, so this is now AB3E. So we have our 3 atoms bonded, 1, 2, 3, and a lone pair on the central atom, which is at the top. Okay, so that is how you draw AB3E molecule. Next, we have AB2E2. It means we have 2 atoms bonded to the central molecule, and we have 2 lone pairs on the central molecule. So the arrangement of the electron pairs is tetrahedral, but after taking into account the repulsion of the bonding and then bonding electron pairs, we now have a bent structure or molecular geometry for class AB2E2. An example of a molecule with AB2E2 class is water. So we have our oxygen in the central atom, and we have 2 hydrogen atoms bonded to the oxygen, and we have our 2 lone pairs here. Okay, now let's go back to how we draw tetrahedral. We have our central atom, then we have one of the atom at the top, one on the side, at the back, one at the front, and one on the side. So when we have 2, let's go back to AB3E first. How do we draw AB3E? We replace the atom at the top with a lone pair. So we delete this and we replace this with a lone pair. Okay, this is AB3E. Now how do we draw the AB2E2? So instead of replacing the atom at the top, it stays as is. So let's erase this again. So this stay as is, and then we replace these ones here. Where's this now? So we replace the 2 atoms here with our lone pairs. Okay, so this is our bent structure. Or we could actually rotate this one here. So we like to do it like this. We have our bent structure, 8. Then one of the electron pair is in dash or broken line, and one of the lone pair is in wedge line. So you can draw AB2E2 class either this way or using this way. Okay, so next, AB4E, that means we have 4 atoms bonded to the central atom and 1 lone pair on the central atom. So the arrangement of the electron pair is trigonal bipyramidal, and after taking into account the repulsion of the lone pairs and the bonding pairs of electrons, we now have a distorted tetrahedron. A distorted tetrahedron is like a seesaw. Okay, so how do we draw a distorted tetrahedron? Let's go back to how we draw a trigonal bipyramidal. We have our central atom, then we have one at the top, one atom bonded at the bottom, then we have on the side, and we have one at the back, so naka dash line, and we have one projected to the front, so naka wedge line. Okay, so that is our AB5. Now, how do we draw our AB4E? What we do is we replace one of the atoms with a lone pair because now we have one lone pair on the central atom. So, we delete this one and we replace that with our lone pair. Okay, if you have observed, this is like a seesaw, no? So this is where you sit here, no? And this is our fulcrum, no? So this is the side of the fulcrum at the back, and this one is the side projected to the front. Okay, so this is how you draw distorted tetrahedron or an AB4E class. Okay, so we have our atoms here, 1, 2, and then 2 atoms in the fulcrum. One should be in dashed and one should be in a wedge, and the lone pair is on the side, on the left side. Okay, next, AB3E2 means we have 3 atoms bonded to the central atom and 2 lone pairs on the central atom. So the arrangement of the electron pair is still trigonal bipyramidal, and after taking into account the repulsion of the electron pairs, we now have a T-shaped geometry. So how do we draw T-shape? So let's go back to drawing the AB5. We have one bonded atom at the top, one at the bottom, one on the side, one projected to the back, and one projected to the front. How do we draw AB4 again? We remove this atom and replace with electron pair, right? So this is our distorted tetrahedron or the seesaw. Now to draw AB3E2, which is T-shape, what we do is this remain as an atom bonded instead of a lone pair, and these 2 atoms now will be replaced with lone pairs. Okay, so you have a lone pair and another lone pair here. So if you can see here, we have our T shape. Now this looks like a T, right? So we have our 3 atoms bonded here, and the lone pairs are projected. One is projected to the back and one is projected to the front. Okay, so that is how you draw a T-shaped molecule with class AB3E2. Okay. Next, we have AB2E3. It means we have 2 atoms bonded to the central atom and 3 lone pairs. The arrangement of the electron pairs is trigonal bipyramidal, and the geometry assumes, the molecule assumes a linear geometry after taking into account the repulsion of the electron pairs. So how do we draw linear molecule under the class AB2E3? Let's draw the AB5 once again. Have one atom at the top, one at the bottom, one on the side. We have one projected at the back and one projected to the front. So this is AB5. How do we draw AB4 again? We replace this with an electron pair. How about, this is AB4. How about AB3E2? AB3A2 is T-shaped, alright? So what we do is, this is, instead of an electron pair, this is a bonded atom, and we have our lone pair here. That's AB3E2. For AB2E3, this here is another lone pair. So the remaining bonded atoms are the ones bonded at the top and at the bottom. Okay, so this is linear, no? So we have our 3 lone pairs and our 2 atoms bonded to the central atom. So that is how you draw linear molecule with class AB2E3. Next, we have AB5E. That means we have 5 atoms bonded to the central atom and 1 lone pair on the central atom. The arrangement of the electron pairs is octahedral, and the molecule assumes a square pyramidal geometry after taking into account the repulsion of the electron pairs. So, how do we draw square pyramidal? So, let's draw once again AB6 first. Have A in the center and 1 atom at the top, 1 at the bottom, and we have 2 atoms projected at the back or bonded at the back. So we use here broken line or dashed line, and then we have 2 atoms projected to the front, or bonds projected to the front. So we have our 2 atoms here, and that is how we draw AB6. Now when we have AB5E, one of the atoms bonded here, it could be at the top or at the bottom, will be replaced with a lone pair. So let's say, for example, we will replace this at the top. You replace this with a lone pair. This now becomes a square pyramidal. Or we could also, instead of the atom one at the top, we will replace the one at the bottom. We can also do that. So this becomes an atom bonded, and this is where our lone pair is. No? So that is AB5E, a square pyramidal. Next, we have our AB4E2. Here we have 4 atoms bonded to the central atom and 2 lone pairs on the central atom. So the arrangement of the electron pairs is octahedral, and the molecular geometry is square planar. Now, how do we draw square planar? Let's draw AB6 again. We have A in the center, 1 atom at the top, 1 at the bottom, 2 atoms at the back, and 2 atoms to the front. Okay, so how do we draw AB5E first? Again, we either remove the top and replace this with a lone pair, or the bottom and replace this with a lone pair. Now when we have AB4E2, both of these atoms at the top and at the bottom will now be replaced with a lone pair. So only the atoms in the square part, no, the base part of our pyramid will be left. So we will remove this and this one here, and replace this with, oh, what happened? With a lone pair. Okay, so this is our AB4E2 with square planar geometry. Wait for a while. Okay, so this is our AB4E2. Why would... Okay, next. Here we have a comparison of repulsion between bonding pair of electrons lone pair versus bonding pair of electrons, and lone pair versus lone pair of electrons. So first we have our methane. As you can see here, we all have bonding electrons, no? Though I mean those electrons that are in the band, no? So we have our bonding electron here and our bonding electron there. We have our bonding pair here. So in methane, the bond angle is 109.5 degrees. Now, in ammonia, this atom here is replaced with an electron. Okay, so now we have our bonding pair and lone pair. This is lone pair and bonding pair repulsion. What happens to the bond angle here? We have here a decreased bond angle from 109.5 degrees. It has now become 107.3. So meaning our lone pair and bonding pair repulsion is greater than the bonding pair repulsion. Now in water, so instead of an atom here, we now have another lone pair. So we have a lone pair here and another one here. So we have now a lone pair repulsion. And as you can see, the bond angle here is decreased even more, which means to say our lone pair repulsion is the lone pair electrons has the largest repulsion, or the biggest or the greatest repulsion. Okay, so here we have lone pair versus lone pair repulsion, which is greater than the lone pair versus bonding pair repulsion, and which is also greater than the bonding pair repulsion. So how do we predict molecular geometry? First, we draw the correct Lewis structure of the molecule. This is really important, no? That you draw the correct Lewis structure of the molecule. After that, we count the number of the lone pairs on the central atom and the number of atoms bonded to the central atom. This is so we can identify the molecule or the class of the molecule. Remember our A, B, E. So we have our ABE. What happened to this? Here, B stands for the atoms bonded to the central atom, and E stands for the lone pair on the central atom. Okay, next is we use VSEPR to predict now the geometry of the molecules. After knowing the class of the molecule, we use VSEPR to predict the geometry of the molecule. So example we have here, what are the molecular geometries of SO2 and SF4, or sulfur dioxide and sulfur tetrafluoride. So first step is we draw the correct Lewis structure of the molecule. So here, first step in predicting molecular geometry is to draw the correct Lewis structure of the molecule. So we start with the first SO2. Okay, so we have SO2. Let's write it here na lang. So we have one sulfur, and each sulfur atom has the sulfur atom has 6 valence electron. So we have 6. Then we have 2 oxygen atoms. So each oxygen atom has 6 valence electrons. We have 6 times 2. Our total valence is 18 electrons. Okay, so now we draw our Lewis structure. We put sulfur in the center. And then we have our two oxygen atoms. Sulfur is less electronegative than oxygen atoms. You can choose, you can look at the electronegativity values of these two if you have periodic table. So next we connect the atoms with a single bond, and then we complete the octet on all the atoms. So for sulfur, since it has two single bonds here, which means it has four electrons, so it needs two lone pairs or four more electrons to complete its octet. For oxygen atom, here we have a single bond, which means na siya two electrons, so it needs six additional electrons or three lone pairs to complete its octet. Same with the other oxygen atom. Okay, so now we count if the number of electrons in this structure is equal to 18. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Since we have 20 electrons in the structure, we have to form double bond. So where can we form double bond? We can have it between this sulfur and this oxygen atom, or with the oxygen atom on the left. Now how do we form double bond? Again, we remove the lone pairs. For example, if we form the double bond between this sulfur and this oxygen atom, so we remove a lone pair of each, and then we form the double bond. What happened? Well, let's rewrite that. Okay, so we have our SO2. Again, we have one sulfur, so we have 6 times 1, 6. For the two oxygen atoms, we have 6 times 2, so we have 12. The total is 18. And then we have our sulfur here, our oxygen atoms. So again, we form double bond because we have too many electrons in the structure. Now how do we do that? We remove, for example, a lone pair of this, and then we form our double bond. So the structure now becomes like this. So only two lone pairs now remain with this oxygen, and a lone pair from the sulfur atom. And for the oxygen on the left, we still have the 3 lone pairs. Okay, so let's recount. If we now have 18 electrons in total in the structure, so we have 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so this is now the correct Lewis structure. So after drawing the correct Lewis structure, we will now identify its class. So we have A for the central atom. B, how many atoms do we have? We have 2 oxygen atoms bonded, so we have AB2. We have 1 lone pair on the central atoms, we have E. Okay, so our class SO2 is class AB2E, and based on VSEPR, AB2E is bent. So to draw SO2, we have our sulfur in the center, and then we have our 2 oxygen atoms and lone pair on the sulfur. Then we complete the lone pair on the oxygen as well. Okay, so that is SO2, the molecular geometry of SO2, which is bent. Okay, next, for SF4, we have 1 sulfur atom. So the valence electron of sulfur is 6. We have 4 fluorine atoms. The valence electron of fluorine is 7. So 7 times 4, we have 28. The total valence electron is 34. So then we draw the skeletal structure with sulfur in the center, and we have our 4 fluorine atoms. Then we connect each with a single bond, and we complete the octet on the atom. So for fluorine, since we have now a single bond, we need 3 lone pairs or 6 electrons to complete its octet. This is the same for all the fluorine atoms in the structure. Okay, now let's count the number of electrons. We have 2, 4, 6, 8, 8 for this, another 8, another 8, another 8. So we have 32 electrons in total, but our computed valence electron is 34. So where do we put another 2 electrons? We can actually put it on the sulfur. Remember the exceptions to the octet rule? We have there the expanded octet, meaning the atom can have more than 8 electrons if the atom is in the n greater than 2, or from third period down the group. Sulfur is in the third period, so it can have more than 8 electrons surrounding it. Fluorine, on the other hand, is in the second period, so it should only have 8 electrons. So now we have this 34 electrons in total, so this is now the correct structure. Next, we identify its class. So we have A, B. Since we have 4 atoms bonded, we have A, B, 4. And since we have one lone pair on the central atoms, we have E. That's A, B, 4, E. And based on VSEPR, this is, what is this? This is distorted tetrahedron or seesaw. Distorted tetrahedron or seesaw. How do we draw seesaw once again, or distorted tetrahedron? We have A in the center, and then or instead of A, we use the sulfur. So this is S, and then we have F, another fluorine atom. We have our lone pair here, and then we have one fluorine atom at the back and another fluorine atom at the front. Okay, then we complete the octet on fluorine atoms. Okay, so this is now our distorted tetrahedron geometry for SF4, or sulfur tetrafluoride. Okay, so we have AB2E bent and AB4E distorted tetrahedron. Okay, so that's it for lesson 3.